Okay, welcome back everybody. In the previous video I said that we needed to come up with better ways of describing organic molecules to each other, so I'm going to go over some of the ways that we can do this. The first way we are already familiar with, and that is just writing a simple molecular formula. As an example, we can write the formula for C4H10 like this. Every method that I'm going to describe has its good points and its bad points. The good point, the primary good point for writing a molecular formula is it's simple. It's easy to write this out, it's easy to read it, and it's easy to write it. You just write the letter C, subscript of 4, you write the letter H, subscript of 10. Everybody knows you have 4 carbons and 10 hydrogen atoms in your molecule. The bad part about it is that the formulas, the simple formulas, can be ambiguous. In other words, sometimes, many times, if I write a simple formula like C4H10, you don't know what type of molecule I'm talking about. This is C4H10, this is also C4H10. So this formula all by itself isn't good enough to tell you all the time what kind of molecule I'm talking about. So that's method number 1, has its good points and bad points. Method number 2 is called writing an expanded structure. So you can imagine that we all got together, we formed a committee, and we said we need to come up with a way to describe organic molecules to each other. And as a committee we say, all right, we're going to pass a law, and whenever someone describes an organic molecule, the way that they have to do it is they have to just write down every single atom that is in the molecule all by itself, and they have to write down every single attachment that all of the atoms have. And if we do that, nobody's ever going to be confused. And this method that I just described is called writing an expanded structure. And you have already seen that because that is what I have been drawing. The good part about it is that it's clear. Nobody's ever going to be confused. The bad part about it is that it's tedious. It is a pain in the ass to keep writing expanded structures, especially for big organic molecules. So this is an expanded structure. I wrote every single atom. I wrote every single attachment. You can pause the video and refer to this or your sheet of paper and figure out what its name is. On pausing the video, this is butane. This is also an expanded structure. You can pause the video and think about what the name of that molecule is. You can refer to that table over there. Well, looks like 6 carbons in a row in this organic molecule, so that must be hexane. This is the expanded structure for hexane, and this is the expanded structure for butane. This is also an expanded structure. This molecule's simple formula is C4H10. We haven't given it a name yet. It does have a name, but all I want you to know is that it's also an expanded structure. Hopefully you can appreciate that, yes, it's clear, but it's also tedious to write every single atom out and every single attachment out. There's a third way, and the third way is called writing a condensed structure, and it's similar to the expanded structure. The good part about it is that it's clear, and it's unambiguous, or usually unambiguous. The bad part about it is it's a little bit better than condensed structures, but it's still a little bit tedious. And let me explain what a condensed structure is. This is the expanded structure for butane, because butane has 4 carbons in a row, and this thing has 4 carbons in a row. This is the condensed structure for butane. You can hopefully appreciate that this is a little bit easier to draw than this, but they mean the same thing. When you write a condensed structure, what you do is you look at every carbon atom individually. You ask what is directly attached to it. Well, this first carbon here has 3 hydrogens directly attached. So instead of drawing 3 H's, I'm just going to write a capital C for the carbon, and I'm going to write H with a subscript of 3. That means the same thing as this over here. Then you look at your second carbon. You say how many H's are directly attached there? Well, there's 2 hydrogens. So you write a C and an H2, and since this first carbon and the second carbon are attached to each other, you put a little dash in between. And you just keep going along the molecule like that. Third carbon has 2 hydrogens attached, so you write CH2, write another dash there. The final carbon, the fourth one over here, has 3 hydrogens attached. Write a C, you write an H3, and you put a little dash there. If you had a choice between writing the expanded structure for butane or the condensed structure for butane, you would probably choose the condensed structure just because it's a little bit easier on your hand, right? There's less stuff to write. Even this, though, is a little bit tedious after a while. The organic molecules can get big enough that even this is a pain to draw. So here are some more examples of condensed structures. This is the expanded structure for hexane because it has 6 carbons in a row. This is the condensed structure for hexane. All we're doing is making a little map between the expanded structure and the condensed structure. This thing here goes there, the second carbon goes there, and on down the line. This is the expanded structure for that mystery molecule that I keep talking about, whose formula is C4H10 but is not butane. This is the condensed structure. This is the same molecule up here, but what I've done is I've not drawn every single H. I've just drawn H3 on the edges, and then this carbon has only one hydrogen, so I drew an H there. So these are just examples of condensed structures. And as I mentioned, even writing condensed structures can be tedious once the molecules get big enough. So there is another way of describing organic molecules to other people. And this way has a couple of names. I'm going to call it a skeletal structure. Sometimes your book might call it a line angle structure. This is a little bit weird. It takes a little bit of getting used to, but this is the way that most chemists use to describe organic molecules to each other. The good part about it is that it is also clear and unambiguous once you get used to it. The bad part about it is that it's a little weird. So I'm going to describe the rules for writing a skeletal structure. They may not make complete sense to you, so just kind of go with it until we get to the examples. Like I said, real chemists use skeletal structures. Because organic molecules have a lot of carbon atoms, that means usually you end up writing the letter C a lot when you draw these molecules. So one of the rules for skeletal structures is you almost never write the letter C. There's another way of telling people where the carbons are. They are implied as corners and sometimes endpoints, and you'll see that in examples. So this doesn't necessarily have to make sense at the moment. You do write all of the bonds in your molecule. If there's a single covalent bond, you write one line. If there's a double covalent bond, you write two lines. If there's a triple covalent bond, you write three lines in parallel like that. Because organic molecules tend to have a lot of hydrogen atoms, with a lot of ways of writing these things, you write the letter H. With skeletal structures, you almost never write the letter H either. So you're almost never writing the letter C, you're almost never writing the letter H. Because you're frequently not writing C's and H's, if your organic molecule has something other than a C or an H, if it has an oxygen, if it has a fluorine atom, then when you draw the structure of your molecule that has an oxygen, you have to write the letter O wherever the oxygen atom is. If your organic molecule has a fluorine atom, you have to write the letter F wherever the fluorine atom is. Because since you're almost never writing C's and H's, you have to tell people where the other kinds of atoms are. You'll see this in examples coming up too. Like I said, every other element other than carbon and hydrogen is drawn. You write the symbol for the element. Here we go with some examples. This is the expanded structure for butane because it has 4 carbons in a row, and butane has 4 carbons in a row. This is the condensed structure for butane. It has 4 carbons and the hydrogens are stuck wherever they're stuck. This is the skeletal structure for butane. You can see that it looks different, but if you get used to this, it's conveying the same information. There are no C's written here. There are no H's written there. But the way that you're supposed to look at this is you're supposed to say, hey, there's a corner here and nothing is written. Because nothing is written and there's a corner, there must be a carbon there. There's another corner here with nothing written. There must also be a carbon there. There's an end point here where nothing is written. There must be a carbon there. And there's an end point here with nothing written. There must also be a carbon there. So once you get used to this, you look at this little zigzag line and you say, oh, there's got to be 4 carbons there. You can see that the first 2 carbons have a single covalent bond connecting them because there's one line there. You can see that the second and third carbons also have a single covalent bond. And you can see that the third and the fourth carbons also have a single covalent bond. Now, the last thing we need to talk about is where did the hydrogens go? Nobody wrote an H. The way that you figure out how many hydrogens are stuck everywhere is you do this. You look at this first carbon, I'm going to draw the letter C, and you say how many lines are going into this carbon at the moment? Well, there's one line going in. There it is. There's the one line. So one line going in, but how many bonds does a carbon atom have to make? Well, it's got to make 4 bonds, right? There have to be 4 lines going in, but I only see 1. That means that 3 of them are missing. And what that means is those 3 that are missing are connections to hydrogen. So there must be 3 hydrogens attached to that first carbon. And you just do this with every other kind of atom. There's a carbon here. How many lines are going in? Well, there's 2. There's 1 right here. There's a second one right there. So 1, 2. But carbon has to make 4 bonds. So you can think, oh, I must have forgotten to write the other 2 bonds that that carbon makes, so there must be 2 H's stuck to that second carbon. You keep doing this. This third carbon has 2 lines going in. There's line number 1, line number 2, but there have to be 4 lines going in, so there must be 2 hydrogens stuck to that third carbon as well. And then this fourth carbon over here, there's 1 line going into it that way, but there should be 4 lines going in, so there must be 3 hydrogens stuck there. And so that's how you interpret a skeletal or a line angle structure. You look at this zigzag line and you say, oh, there's 1, 2, 3, 4 carbon atoms, so the molecule has a formula of C4. This carbon here must have 3 hydrogens stuck to it. This one here must have 2. This one here must also have 2 hydrogens. This last carbon must have 3. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogens total. So this molecule's formula is C4H10. So that's an introduction into a skeletal structure. Just to confuse things a little bit, this is also the skeletal structure for butane. Sometimes people think that it looks prettier to draw the carbons at the very ends. So here I did not draw the letter C, here I did not draw the letter C. Sometimes people think it looks nicer to actually draw the C's at the very ends, so they draw them. The other general rule is if you have hydrogen atoms that are stuck to an atom and you actually drew the letter for the atom, see how I drew the letter C here? Then you put the hydrogens in as well. That's also a general rule. So because there are 3 hydrogens stuck on this carbon, and because I actually drew the letter for this carbon, I show people the hydrogens there too. Same thing on the other end. This is butane, this is butane, this is butane, and that's butane. It's just 4 different ways of drawing the same molecule. This is hexane, that's the expanded structure for hexane. You can tell where this is going. This is the condensed structure for hexane. This is the skeletal structure for hexane. 1, 2, 3, 4, 5, 6 carbons in a row. There's 1, 2, 3 hydrogens, 2 there, 2 there, 2 there, 2 there, 3 over there. That is hexane again. And if you don't like that and you think it looks ugly and you want to write the prettier way, this is also hexane. These are just 4 different ways of saying the same thing. Just to drive this point home, this is the mystery molecule whose formula is C4H10. That's the expanded structure for C4H10. That is the condensed structure for C4H10. That is the skeletal structure for C4H10. 1, 2, 3, 4 carbon atoms. If you want to draw the prettier version, this is also the skeletal structure for C4H10. Just to give you a sense of why skeletal structures exist, this is the structure for the molecule in Advil or ibuprofen. This is a pain reliever. So you can see this is the condensed structure over here. And even this is a little bit tedious to draw after a while. You probably don't want to draw that if you can avoid it. This is the skeletal structure for the same molecule. And it's a little bit easier on the eyes. It's a little bit easier to draw. But once you're used to looking at it, you can see where everything is. There are carbon atoms all over the place. There are carbon atoms at all of the corners and all of the ends where I did not bother to write a symbol. There they are. But over here there's an oxygen atom, so I have to draw the O. Over here there's an oxygen atom, so I have to draw the O. There's a hydrogen stuck to the oxygen, so I'm going to draw that too. And you can see all sorts of other stuff. You can see, well, double covalent bond, double covalent bond, double covalent bond, double covalent bond to the oxygen. And the hydrogens, you can figure out where they are just by playing the game that we played. So for example, I'm not going to do that for all of them, but this carbon over here, how many lines are going into that carbon? Well, there's 1, but carbon has to make 4 covalent bonds, so there must be 3 hydrogens stuck to it. And if you look, there are 3. 1 more. This carbon over here, how many lines are going into it? Well, 1, 2, 3. How many bonds does carbon have to make? It has to make 4, so I must be missing 1, so there must be 1 H stuck to this carbon over here, and there is. You can just keep doing that with skeletal structures. This is a little bit of practice. You can pause the video and try to figure out what the formula of this molecule is. So what's the formula for this molecule? Unpausing the video. First thing we have to do is we have to find the carbons. There's a carbon here. So any place where there's an end where there's no letter, and any place where there's a corner where there's no letter, there's a carbon atom. So there's a carbon there, carbon there. So that is 1, 2, 3, 4, 5, 6, 7 carbons. So we already have part of the formula, C7. There's also an O, right? There it is. So we've got the O. The only thing we have left to do is we have to figure out how many hydrogens are on this sucker. And this is a little bit tedious, but this is what you do. You look at the first carbon. You say, how many lines are going in? Well, there's 2. How many bonds does carbon make? 4. So there must be 2 H's stuck to that carbon. This carbon over here, how many lines are going in? 1, 2, 3. But every carbon has to have 4 lines going in, 4 bonds. So there must be 1 H stuck there. This carbon here, how many lines are going in? 1, 2, 3. So there must be 1 H stuck to that carbon. This carbon here, how many lines are going in? Just 1. So there must be 3 H's there. This carbon over here is the same kind of carbon up here, so there must be 3 H's there as well. H, H, H. This carbon is the same kind of carbon as well, so there must be 3 H's there. This carbon here, how many lines are going in? 1, 2, 3, 4. So this carbon at this intersection has no hydrogen stuck. I think we're done. I think we covered all the hydrogens. Now we have to count them up. 2, 3, 6, 9, 12, 13, 14. So the formula for this molecule is C7OH14. Probably it would be written C7H14O, but I don't really care about what order you write them in, as long as you get the numbers of them correctly. Let me just double check. 2, 3, 6, 9, 12, 13, 14. Yep, we are correct. So now you're a pro. You can look at this molecule, and if you spend a couple of minutes on it, you can figure out that the formula for that molecule is C7H14O. What's even worse, and everybody's going to groan, or mentally groan when I say this, imagine that you're taking a quiz or a test, and you see this molecule here, and I say, what is the molar mass of this molecule? Now, maybe this seems like a ridiculous question, but it's not that difficult to answer as long as you can figure out the formula. So it was C7H14O. Once you have the formula, then you can just look up the molar masses in the periodic table. So it's going to be about 12 grams times 7, plus 1 gram times 14, plus 16 grams times 1. You add them up, and you can figure out the molar mass just by looking at this picture and having a periodic table with you. There is one other way that we are going to talk about for describing organic molecules to each other. That is going to get its own separate video. That other way is giving every organic molecule its own special name. There are a lot of rules that you need to know for how to give different organic molecules their own special names, so we're going to cover that in actually a bunch of different videos. But that's the end of this video. We covered molecular formulas. That's one way of describing organic molecules to each other. We covered expanded structures. We covered condensed structures. And we covered skeletal structures. That's it. See you in the naming video.